y squared plus z squared dm. And the same for yy for the other dimension, zz the other dimension. For the products of inertia, ixy, from this definition, it's the negative of x times y dm. So you're simply adding all x's and y's weighted by the masses. So the masses favor some positive x's and y's over the other side, you'll get a negative.
So it depends on the coordinates.
Yes, exactly. Exactly, and this is why one of the legitimate questions that we can look for next is there is set of coordinates over which these products of inertia vanish completely. We can talk about this later, which we call the principal coordinates.
So this is a symmetrical, it's
Yes, it's symmetrical around the diagonal. Yes,
okay.
The matrix is called I. Ijk is Ijk. If you like this notation. Any question, please? Yes.
And the reason why I pull out the omega is because it's not dependent on that.
This is very good. So this is why we did this trick. With mathematical trick to write the cross product term in terms of matrix multiplication, because this before was r cross omega cross r. So omega in the middle, I cannot get outside. But after doing this, now omega is on the side, I can get it outside of the integration side. And now I'm integrating simply on over coordinates, local coordinates. Okay? And this is why now for anybody, irrespective of the motion, we have characteristics for the body, the moments of inertia. So for a rod, for example, some examples for moments of inertia. Here is a rod of mass m and length L. We're interested in the center of mass. So here it is in the middle. I have three axes, one longitudinal and two lateral, 2 and 3. Okay? So I11 for this guy is 0, I22 and I33 is the same, and they equal to ml squared over 12. Okay? Irrespective of the motion, I don't care. This guy will always have these moments of inertia about the center of mass. But the axes have to be associated with the body, have to be body axes. The other products of inertia vanish. I1, 2, I2, 3, they all vanish here. And if you have a disk, for example, similarly, two axes in the plane and one out of the plane, I11 equals I22, of course, because they are similar, no preference. This is mr squared. R is the radius, obviously, over 4. And I33, like any axisymmetric shape, you just add I11 and I22. So mr squared over 2. You can have a sphere. These are the common shapes. You need to know these things. Of course, you can go and derive these expressions using the basic principles. Okay? You can derive these expressions, and probably you did that in your undergrad. If you didn't, I don't care, we will negotiate. So this is probably 1, 2 is in the plane, and 3 vertical. And in the sphere, everything is in every direction is the same, right? So no preference at all for 1 or 2 or 3. So for sure they have to be equal. 2 over 5 mr squared. Obviously, r is the radius of the sphere. Any question? Yes.
the two, axis 2 is actually going.
Which one? Which one?
Sorry, I don't really understand the 1, 2, 3. So that 2 is going into the.
This is basically you can define this one to be 1, this is 2, and this is 3. It doesn't matter, but stick to these things. What I'm saying is that if you call this, where is it? Okay, if you call this 1, then in your notation, I11 will be ml squared over 12. You see what I'm saying? Yeah, but the naming is arbitrary. It's up to you. Or you're going to have a problem to show that. Any question?
If the 1, 2, 3 is the same of x, y, z in the coordinate.
Yeah. The naming is arbitrary. Yes. I'm going to continue examples.
Question?
Examples of common shapes. So what else? Maybe plate, for example, or cylinder. And actually you can add things. So here is for the center of mass for the middle, say 1, 2, and 3, the longitudinal axis. Its length L, and mass M, and radius R. Okay? Okay? So I11 is the same as I22. And what's that? As a rod, actually, it's ml squared over 12. And as a disk, right, it's mr squared over 4. Yeah, that's right. And then I33, as a rod, this is the longitudinal axis of the rod, so there is no contribution, it's 0. But as a disk, it's the mr squared over 2. Either you construct it the way I'm describing it, or you just know it from here. For a cylinder, here is the formulas for the moments of inertia. Barometer, you will be allowed to do a formula sheet on your own. It's up to you totally. Put this information or just points. It's up to you. So maybe last thing, common example, plate. So this is probably L, W, again, 1, 2, and 3. Remember the definitions. The definitions, Ixx is the square of the other dimensions, the perpendicular dimensions. So the perpendicular dimensions to the axis 1 is this guy, right? The W and the thickness, but the thickness is negligible. So this is mw squared over 12. Same for 2, is also ml squared over 12. And for 3, it's both. Right? Any question? Any questions? Yes.
Where does it come from that from?
You can derive it like I said. You can derive this using the basic definition, and you will find this instantly. You can come to our website, drive it out, not just waste some time to do it here. But this is what we had seen in undergrad, how to use these definitions to come up with this. Okay? Yes, please.
In most real case, disk and plates are not realistic.
What do you mean?
Because for disks, right, there's no thickness for.
The thickness is negligible. So it's as if you use the main definition, you'll have here thickness square. But the thickness is much smaller with respect to the radius, so you can neglect t squared with respect to r squared. So yeah, these are idealized shapes. Okay. If you have a more complicated shape, so either mix and match and add moments of inertia, that's perfectly fine, or use the basic definition to get it for your shape. Okay, so this is the moment of inertia concept. Any question about the moment of inertia?
What about the cross products of this inertia matrix?
Say it again, please.
The other products of this inertia matrix.
Yeah, here in the examples,
Yeah.
the products of inertia, so they are all zeros here because these are symmetric shapes.
But if you
Whenever you
have,
have a symmetric shape, then it's.
but if you have to calculate, we are going to do some example in which we have to calculate it.
Well, for the common shapes, the idealized shape, most of the idealized shapes are symmetric, so they are zeros.
Like it sometimes happens.
And
that
I'm not
two of the-
gonna visit you on by bringing some funky shape. It's not. This is not the point of this course. You should have seen it before and how to do the product of inertia using the basic principle.
For the
So as
symmetric,
far as problems are concerned, because I know that you guys are asking about this, as far as problems are concerned, you need to know these shapes. But as far as your dynamics knowledge, yeah, you need to be able to know how to use these definitions, these black ones, to get these formulas, which you did in your undergrad. Yes, Joseph?
for the symmetric shapes, if the axes are not aligned with the axes of symmetry, then do the other terms show up?
Exactly. And this is, like I said, invokes the problem of, okay, how can I rotate my axes to get a set of axes over which the products of inertia completely match, which they are called the principal axes. And we will tackle this problem here, but after talking about the rotations itself. We didn't introduce rotations yet. Next section. Okay, so for me, so far, for dynamics, all what I have introduced newly here is simply the angular momentum for a rigid body is written as I omega. Okay, this is all what I introduced new. I is an inertia matrix full of 9 numbers. Probably 6 of them will be zeros if my shape is nice, but I need to know the other 3. Okay? And omega is the components of your angular velocity vector. This equation is indeed in the body axis. Okay? This is not true in any other axis. The angular momentum in the body axis equals the inertia matrix in the body axis. This is why I indicated the body axis here. That is omega components in the body axis. Okay? And in dynamics, we're always interested in the rate of change of this quantity. I know from the beginning that hc dot equals what? Hc dot equals what? The rate of change in angular momentum is what?
Angular moment.
The moment, right? So this is, particularly for the point C, this is simply the moment C, the moment about C, correct? And now I know that hc is equal to this, I'm going to differentiate it. Knowing that this is written in the body axis, and I'm differentiating with respect to what?
Inertia.
Always inertia. Let's differentiate this guy. What do you think about I, the values of the moment of inertia, written in the body axis? What do you think? This guy is rotating in a motion, but I'm always focusing in the body axis. I11 will always be 0, I22, I23 will always be this, right? So the values of the moments of inertia in the body axis, they are constant by definition, right? So there is no derivative here, so I'm going to differentiate this guy only. So this is I, C, omega dot, This is in the body axis. So HC is defined in the body axis and differentiating with respect to inertia. That's fine, differentiate your components in the body like I did, but you have to add omega cross your vector, which is, my vector is actually I omega, okay? This is indeed equal to the moments about the center of mass. Remember this equation, H but rate change angular momentum equal to the moment. This is not true about any point. It has to be the center of mass. The center of mass is unique. Okay? This set of equations which I just boxed, this is called Euler's equation for rigid body. Rigid body dynamics or rigid body rotation. Okay? It's not new equations, it's just a way you're writing it. You just come from the rate change angular momentum equal to the moment. But we're writing it in a nice way because everything is written in the body axis, which is typically the case. Any question? Let's have one example. Okay. Okay. This is example 8 to in green. It says a thin uniform bar of mass m and length L. This guy is mass m and length L. Is connected by a pin joint. So there's a pin joint here. This is a pin allowing you to rotate about one axis, preventing all the other degrees of freedom. A pin joint at one end to a vertical shaft, which rotates at a constant rate omega